This is a video on section 11.3 related to the dot product. Okay, the dot product. The dot product is an operation on vectors. Okay, and vectors we introduced in the previous section. So, for example, recall that you could have the vector v would be maybe say the vector 1, 2, 3, and maybe you have a vector w is say maybe 3, 4, 5. Okay, recall where these come from geometrically. Recall that the vector v can be thought of as the vector from the origin O to the point V, okay, where the vector between O and the point V is V minus O. So for example, the origin O could be the point 0, 0, 0, and the point V could be 1, 2, 3. And the way we interpret these vectors as in the XYZ space, here is your origin O, here is your point V to be 1, 2, 3, which you obtain by going 1 in the X, 2 in the Y, 1, 2, 3 in the Z. That will get you here. So there's your point V, and your vector V is this object right here. Here's your vector V. Okay, so if we were looking at this in Mathematica, for example, I could do the origin O would be 0, 0, 0, and the vector V, I'm sorry, the point V could be 1, 2, 3. Okay, and if I want V thought of as a vector, I would do V minus the origin. Okay, and now we have point origin, the point V, and now the vector V. And if you want to plot these objects, you do this via the graphics 3D command. And if you want to view O as a point, you say point and tell the computer to view O as a point. If you plot that, there is your point for the origin. Okay. If you'd like to plot both the origin point P and the point V together, put squiggly brackets to tell the computer that you're going to do multiple things and say point V. Okay, and now you have two of these points right here and right here up in the corner. Okay, and if you need, you can include axes label goes to XYZ so we can see. Oh. Axes goes to true. Alright, hold up. There we go. So you gotta put some axes and then put the labels on them. Okay, so here are 2 points, X, our point O and our point V. If we want to plot the vector V, you view the vector V as an arrow, and it's a arrow that starts at O and ends at V. Oops, I need to put the points in squiggle brackets here. Okay, so this arrow here is the vector from the origin to the point V. This arrow is your vector V. Okay, so that's what we have here. To do the dot product, we need to first have some vectors to be given to you. So these will be given in some way. Okay, now let's define the dot product. Define the dot product of the vector V with the vector W. And it's simply written with a dot. Okay, we know how to add vectors and do scalar multiplication of vectors. So now we're writing down a way to multiply 2 vectors. And the way we're going to multiply, this means define equals. I'm about to define how to compute the dot product. It'll be the first entry of the vector V multiplied by the second entry of the vector W. Add together the second entry of the vector V, second entry of W, third entry of V, third entry of W, and add them all together. So for example here, if V was 1, 2, 3, and W was 3, 4, 5, then V dotted with W would be 1 times 3 plus 2 times 4 plus 3 times 5. And you would get 3 plus 8 plus 15 and whatever that is, 26 I think maybe. Yeah, 26. Okay, so the thing to note here, very important thing to note, is the dot product takes two inputs, and both of those inputs are vectors, and what comes out is a number. Okay, now from this dot product, okay, we can now, just this simple operation of the dot product, we can now define the length of a vector. And the length of a vector, or the magnitude, is denoted by this, for example, the two brackets, or you may just see a single bracket, kind of like the absolute value. But this is the length or the magnitude of the vector v, and it's defined to be equal to the square root of v dotted with v. So, for example, if the vector v is 2, 0, 0, then the length or the magnitude of the vector v is the square root of v dotted with v, which is the square root of 2 times 2 plus 0 times 0 plus 0 times 0, and you get the square root of 4, which is 2. Now this operation should hopefully make sense, because if you consider what this vector v looks like, this is the vector here. Our vector v was this vector that goes 2 steps from the origin in the x direction. Okay, and the length of this vector, right here, the length of it is 2. And that was this result here. So this definition for magnitude or length of the vector makes good sense. Okay, so we can use this result for the length of the vector to help us give a more geometric meaning, geometric understanding of the dot product. So the dot product is just this operation that I've defined, and you get a number, and it's not really very meaningful as a number yet. So let's see if we can build up a geometric meaning for the dot product of two vectors. Okay, so let's say that our vector v, okay, let me just think that these vectors, just for illustration purposes, are vectors in the xy plane. So here is the xy plane. Here is the vector v, so there's the point v, v1, v2. Okay, here's the origin. Here is the vector v. V vector is equal to v1, v2. Okay, and we know that the length of this vector is the length of v. So the length of v is the length of that arrow. Okay. Now, continue the idea here to draw a circle that has this vector, and you're going to swing this vector around by an angle theta. So this vector will trace out a circle of radius length of v. Okay? So this point here, why it's called v1, v2, you can also denote it as the length of v cosine of the angle, length of v sine of the angle. This is just trigonometry. This is the description of a point on this circle of radius length of v. Okay. Now there's also a vector w over here. Okay. Here's w. W may be a circle of a different radius. Okay. So this point here, okay, this point here could be denoted as the length of w cosine of its angle psi. So maybe there's a different angle to it, cosine of psi, length of W, sine of psi. Okay, and now we can go ahead and compute the dot product of these two vectors, v dotted with w, okay, is going to be the magnitude of v cosine of theta, magnitude of v sine of theta, dotted with magnitude of w cosine of psi, magnitude of w sine of psi. Now compute this dot product out. Okay, via the mathy definition, it's going to be this multiplied by the first entry plus the second entry multiplied by the second entry, and add the results. You'll get the magnitude of v, magnitude of w, cosine of the angle theta, cosine of the angle psi, plus magnitude of v sine of theta, magnitude, let me just put all this in a single computation here, magnitude of w sine of theta, magnitude sine of psi. Okay. Now the magnitude of v, magnitude of w is in common, so I can factor it out. And I get cosine of theta, cosine of psi, minus sine of theta, sine of psi. And if you remember your trig identities, the thing in square brackets there is the same thing as the cosine of psi minus theta. Okay. Where psi minus theta is the angle right here between those two vectors. Okay. So you get the magnitude of v, magnitude of w, cosine of phi, okay, where phi is the angle between the vectors v and w. Okay, so let me move to the next page and summarize this formula that we've just done here. But this computation is going to give us the geometric meaning that we are looking for the dot product. Okay, so what we've just shown here is that v dotted with w has a mathy definition. It's v1 w1 plus v2 w2 plus however many of those you need. And it also has definitely a more physics meaning, in that it's the length of the vector v, length of the vector w, cosine of phi, where phi is the angle between v and the vectors v and w. Okay. Now this is a crucial result. So v dotted with w, length of v, length of w, cosine of phi. This one is a very crucial result. Let's take a look at maybe an example here illustrating this result. Okay, let's say that the vector v is 1, 0 and the vector w is 0, 1. Okay, if you plot these, okay, here's your vector v, here's your vector w. These two graphically look to be at a right angle, so phi is 90 degrees or pi over 2 radians. So the cosine of that 90 degree or pi over 2 radians is cosine of pi over 2 is 0. So now we know that the dot product v dotted with w, the mathy way, is 1 times 0 plus 0 times 1, or it's the length of the vector v, which is 1, the length of the vector w is 1 times the cosine of pi over 2. And in both cases you get 0. Okay, so here this mathy way you just get the number 0, but here we can see why the answer is coming out to be 0, and it's because these two vectors v and w are perpendicular to each other. So the conclusion we can draw here is that two vectors, v and w, are perpendicular. Our textbook uses, instead of perpendicular, they also use the word orthogonal. Both mean the same thing. Two vectors v and w are perpendicular or orthogonal if and only if v dotted with w, the dot product, comes out to be 0. Okay, so this will give you a nice way to build up some understanding of the dot product. So for example, if I have the vector 1, 0, 1, and I have the vector w equals 0, 5, 0, right? You know, these vectors live in 3 dimensions, but we can see here that this vector w is in the xz plane, and it's 1 over and 1 up. So here's your vector w, and it is in this plane. This is your vector v, sorry. And your vector w is in, which direction is that in? 0, 5, 0. So it's 5 steps in the y direction. So here it is. Right? So if you turn these vectors, you can see that v dotted with w, the picture is kind of hard to tell, maybe that they're perpendicular, but v dotted with w comes out to be 0 plus 0 plus 0. So you get 0. Since this dot product came out to be 0, you know that v is perpendicular to w. And that makes sense for this example because this vector v, you can see that it's down here in some plane, and the other vector is pointing up like this. So they are in fact perpendicular to each other because one is in the plane and one's pointing in the exact opposite of the direction of that plane. Okay, so this is an introduction to the dot product as an operation on two vectors and the two different notations, or the two different ways here of computing the dot product. Okay, so this formula, physicsy formula, leads us in the direction of another very important result. You know, what if you want to find the angle between two vectors? So let's say that you have two vectors. Okay, so maybe v is over here, maybe w is this vector. What is the angle between these two vectors? Well, it's a pretty straightforward computation. W is given and v is given, so you know these two things. The only thing you don't know is the angle phi. So if v is given to you, then you can find the length of v. So this will essentially can be found. It's not given. It can be found. Okay. If w is given, by a similar fashion, w can be found. And if v, the magnitude of v, w, and the magnitude of w are all known, then the two vectors, you can take these to compute their dot product. That can be found. Okay, and now you have enough information to take the previous formula we had and rearrange it to v dotted with w divided by the magnitude of v, magnitude of w. And all these entries are known. So this will tell you that the angle phi between two vectors is the inverse cosine of the dot product of the two vectors divided by the two magnitudes multiplied by each other. Okay, so this is a second crucial formula that comes out of this section. So this formula is the important one, the notion of the dot product of two vectors, the physicsy way, and we had, well, the magnitude of a vector v is the square root of the dot product. Okay, so these were our three important formulas for this section 11.3, and the rest will just be some practice from your homework.